Imagine a calculator that adds 2 plus 2 and sometimes gives you 4 but other times gives you 5. It is running, it looks fine, but the result is completely wrong. What happens when our digital tools, from financial models to navigation systems, operate with flawed reasoning, producing results that are technically generated but fundamentally incorrect? When software generates wrong algorithmic outcomes, it is primarily due to what we call logic errors. These are not crashes or syntax mistakes, but rather deeply embedded flaws in the underlying instructions or design of the algorithm itself, causing the program to run exactly as coded, but not as intended. The core mechanism behind these errors lies in the very nature of algorithms as step-by-step instruction sets. If these instructions fail to accurately model the real-world problem they are trying to solve, or if they contain intrinsic inconsistencies, the output will inevitably be wrong. One common cause is incorrect assumptions. A programmer might assume that a certain input will always be positive, or that a user will only follow a specific path, leading to unexpected behavior when these assumptions are violated. Another significant area is flawed business logic. This occurs when the rules or calculations implemented in the algorithm are themselves wrong or incomplete, meaning the software is performing the intended calculation perfectly, but the intended calculation was incorrect from the start. We also frequently encounter off-by-one errors, where loops or array indexing iterate one too many or one too few times. Think of a list of 10 items where the code only processes 9 of them. Similarly, using the wrong comparison operators, such as greater than instead of greater than or equal to, can subtly alter decision points within the algorithm. The order of operations is another subtle trap, where mathematical or logical operations are performed in an unintended sequence, leading to skewed results. Furthermore, data type mismatches or overflows can cause significant problems, especially when handling large numbers or precise calculations, potentially losing precision or wrapping around to unexpected values. Finally, unforeseen edge cases are notorious for producing wrong outcomes. An algorithm might work perfectly for typical scenarios but completely fail when confronted with unusual or extreme inputs that the original design did not account for. All these issues representing flaws in the thought process or translation of intent into code, rather than outright coding mistakes that stop the program from running. To tackle these elusive logic errors, a multi-pronged approach is essential. Systematic testing is your first line of defense. This includes writing detailed unit tests that verify individual components, integration tests that check how different parts work together, and crucial boundary condition tests that specifically probe those tricky edge cases. Beyond automated checks, thoughtful code reviews and pair programming sessions are invaluable. Fresh eyes can often spot logical inconsistencies or flawed assumptions that the original developer overlooked. Most importantly, robust algorithm design should always precede coding, ensuring that requirements are clearly defined and the algorithm structure is thoroughly considered before a single line of code is written. When an error is suspected, debugging tools become indispensable for tracing the execution flow and inspecting variable values at each step, allowing you to pinpoint exactly where the logic diverges from expectation. It is interesting to note that these types of errors often lead to what are called deterministic errors. This means they produce incorrect results consistently under the same conditions, unlike non-deterministic errors, which might only appear randomly. Understanding this distinction can significantly help in debugging. The cost of fixing a logic error escalates dramatically the later it is discovered in the software development lifecycle. A flaw caught during the design phase is far cheaper to remedy than one found in production, impacting users. This emphasizes the value of upfront investment in rigorous design and testing. Ultimately, preventing wrong algorithmic outcomes demands meticulous attention to detail, a deep understanding of the problem domain, and a commitment to thorough verification at every stage. By focusing on robust design, comprehensive testing, and collaborative reviews, We ensure that our software not only runs without crashing but also executes its purpose with accuracy and reliability, building greater trust in the digital systems that power our world.
If this helps you fix faster, like, subscribe, and keep debugging with us.